This presentation looks at regenerating hull surfaces from laser point clouds. The area of hull surfaces is somewhat of interest to me, and it's an area that I've been working on for many years. Going forward than just basic surfaces, looking at ways that we can improve and make the definition process more efficient, and that often includes working with data sources that we have available to us, for example offsets and lines plan information. A couple of years back I had the opportunity to work with some laser scan data and develop a solution that worked with that kind of data for my own. That was presented recently in the ICAST conference, and there's much more information can be found on my website in terms of the software that I develop and the types of problems that I like to solve. So if we turn to this particular challenge, the challenge of creating the hull surface from the scan data, I believe I would say it's different challenges to other typical optical survey scenarios. The reason for this is that the vessel is out of the water and is outside of its typical operating environment, so there are things going on while it's being surveyed that aren't really in its real environment. We've been creating good software in the marine domain for hull surfaces for many years, but a lot of the solutions that take laser scan data are generic solutions, and I think that the lack of a crossover at this point means that a lot of the solutions that people are working with are not very efficient. So really what I wanted to do was utilise the best information and the best technology to combine these two areas so that we can deliver the best surface definition in the shortest amount of time. So the storyboard of this presentation will start with having a look at the actual scenario we're working with, the scanning of the ship itself, and we'll look at some of the solutions used to turn that into a hull surface and some of the challenges there. We'll then start looking at my own solution, which is very much a curve-based solution, generating a surface from a set of curves. Some of the challenges involved in turning the laser point cloud into a hull surface definition. And then looking at the validation process to make sure that the surface you're generating is actually the one that you wanted to get and it's accurate to the laser survey scan. So let's start by having a look at the challenge. So here we have a typical scenario. It's a mega yacht in a yard. It's outside. For the most part we can see a lot of the hull form. But there's some things that we need to point out. Obviously, while it's out of the water, it's being worked on. We can see scaffolding and supports. There are areas of the surface that it can't see, for example, under some of the supports. We also must highlight that often in the marine world, when we create a hull surface, we don't want the appendages to be attached. So we can't take the exact surface representation and turn it into a hull surface directly. This particular survey offers us also some interesting challenges. If we look at the top right hand corner, we can see a reflection of a mast in the hull form. It's interesting at this point we see that this vessel has a very shiny surface, and the laser failed to capture anything above the waterline that was having this shiny finish. In fact, on the transom, we see at the stern there, we can't see any of that at all. It's just purely reflecting the white sky. So that is the challenge when it comes to laser scanning. It's literally scanning exactly everything that it can see, and that means including things that you don't want there, or sometimes excluding things because it can't see them. Now if we'll look at the actual surface generation challenge, what happens is that we generate a considerable amount of data, and the challenge is to fit a surface to that data. A typical example, as we see here, is one where the surface has been draped over the surface, and while this is a fairly quick solution, a fairly generic solution, when we start using some marine expertise, we find that this solution isn't particularly useful to us. For example, as a living surface, it's not really got the ability for it to be modified. It's just got too many data points. There are also features on the hull form that we're not really picking out, for example the rabbit line, and the stem aren't really being captured in this surface definition. Which is a shame because it's probably going to be a fairly good quick approximation. The challenge is that we then need to introduce some more tools, some more systems to make it a more accurate surface. So we use solid modelling. We introduce further surfaces and we introduce numerical processes so we can get intersections between the surfaces to create this definition. The challenge is that this surface then becomes more complicated, more challenging to modify, and in some tools that we might want to use to analyse it, it might not be possible to take this data in directly. From a development point of view, myself, surfaces that are defined as solid modelling are more challenging because I have to use a more complicated tool to extract the data from that. So what could we say could be our key actions to improve the situation? Well, first of all, we could take the geometry from the laser scan with the understanding that it will not be perfect. It will contain all the defects that will be there from our scanning environment. And what we could also do is, why not use a mature marine hull surface definition technique to build the surface? So again, we're making that crossover. And the key thing here is also that it's going to be important to validate the surface so that we can prove that what we're capturing numerically, geometrically, is what was surveyed. So let's have a look at some of the innovations I've made and the story behind that. So purely looking at the surface fitting situation, we'll find that most commercial vessels are far more complicated than just a simple rectangular surface. It's quite a challenge to put those two together. In very complicated hull forms like those with the twin skeg, trying to do that with a single surface is very challenging. While it might be possible, it's certainly not a very effective use of our time. Therefore, we use solutions where there are multiple patches and where we can put patches in particular positions. The challenge with this particular case, though, is that to assemble these patches takes a particular type of approach. We can't really assemble each patch case by case because it would take, again, a considerable amount of time. And we need to make sure that all those patches have curvature continuity, tangential continuity where we need it. So that's why we have a curve-based definition. Using curves that can be 3D or 2D on a plane, we can capture the shape of the surface very easily. In fact, this corresponds quite well to typical lines plans. Crossing over to the laser scan, one of the nice benefits is that we can section the laser cloud exactly in the same place where the curves are going to be. So this means that we can extract the data where we put these curves very quickly and very easily. In this respect, what we're looking at is intersecting the laser cloud with a plane and then purely doing a curve fitting exercise. So how can we address those challenges within the surface? For example, this particular case shows that we have some appendages in this surface. So rather than take the whole point cloud, what we could do is selectively sample that cloud, and we can do that with those 2D curves by intersecting it with a plane. And we can choose where we want to put those features. Of course, there's still sampling challenges within this. As we said, with this particular example, we do have areas of the hull form that are not captured and areas of the hull form that are missing. This particular water plane here shows some quite significant gaps when we capture a waterline. We also get challenges from the fact that the vessel is out of the water. Let's have a look in this particular area. We see that once we get to the stern here, we've got the propeller, a section through the rudder. We can also identify that the propeller might have been moved during the sampling process, the scanning. We see on these waterlines here it's picked up the props that are supporting the hull. And in this area here we can see some of the accommodation that was also captured in there, which looks quite nice, but this data is totally useless for what we're trying to do, which is capture the hull form. So what we need are methods that can go into the data and just capture the data that we need. We don't want to take all of the data. So methods of finding practical geometry can be highlighted a little like this. So this is an example of a prop on the side of the hull form. And by surrounding the data with a grid, we can start to look at the connectivity of the data between that. For example, rather than take every data point, we just take a data point within this grid, and it simplifies the amount of data that we need to deal with. We can start to look at the connectivity throughout the grid between these points and identify areas that are disconnected or are a longer way around, and we can exclude that data very easily. So it's again a very simple, elegant filtering exercise. So let's put this whole process together. In this particular case, we're looking at a planar slice some way up on the top of this ship here. This will give us a set of data points that could look like this. We could use a simple fitting algorithm, least squares for example, to generate us a B-spline along this area. This looks fine, but doesn't really capture the kind of details that we would want to include if we were doing this from a marine domain perspective. We are missing, for example, the flat of side, and we're not necessarily capturing data that specifically relates to the rounding of the stem. So this means that in this particular case we only have one data point for all those points that are there at the bow. So how can we look at improving that? Well, one of the benefits of the curve approach is that we have an underlying framework which dictates the kind of properties that we might find on the hull surface. They mark out tangents, flat areas, and any connecting curves will understand the information that you can find there and implement tangents appropriately. So by comparing and using this information along with the point cloud, we can start to mark sections of the point clouds out for having particular properties. So we can identify where the straight bits are, where the rounding areas are, and where the shaped areas are. So therefore we can adjust the fitting algorithm to address those different areas. And that's done by splitting the curve up and applying tangents. So once we've done that, we can then fit the straight area with the straight segment, the shaped area with a shaped segment, and the rounding area with either a blend or a much smaller shaped curve. So what this means is that the curve fitting process is far more sensitive to the shape than if we just use a generic least squares fit, for example. Another thing that we can introduce is the process of slowing the designer down. Now that's useful because we get them to review the geometry that they're generating in more detail. We can get them to review the kind of properties that the software thinks should be being applied. We can have a look at them applying smoothing and making sure all the control points are the right number of points. So if we now go through the process of putting it all together, we'd start with our overall model. But in this case we can only focus on the underwater form because we have really no topsides data. Now we can cut some contours from that and we can start to see the kind of the overall shape of the surface, start to plan where we're going to put some curves. We'll need to start with our boundaries because these will pick out the shape and also assist the fitting process that will come later on. From that we can pick out our diagonal curves in this case and then cross those with the sections, and now we have enough data to create a complete surface. The surface will give us some contours. We can look at the surface, we can validate the surface with respect to its curvature. We can then go on to validate the surface for its accuracy. This particular case here shows the accuracy of the surface within 10 millimeters. We simply shade the surface red when it's beyond that. We also have some white areas. That's the areas of the surface that are transparent because there's just not enough points to really give us a statistical mean position for the surface in space. We can up the tolerance and then we start to track down areas that might be worth improving. By looking at the sidedness, we can illustrate the surface being on different sides of the laser data. Another display that we could look at is whether the surface is actually within the thickness of the cloud. Of course, we can also produce some global statistics which might help give us something that can be reported on, but as far as communicating the areas of the surface that are accurate, the graphical view is very helpful. And obviously this helps the designer track down areas of the surface that might not be so accurate, but it also helps them interact with their manager and with their customer to communicate the level of accuracy that they're achieving. So if we talk about performance, how quick is this? Well, quite frequently we see that to create the shape of the surface, because the underlying data is good, it can take a matter of 20 minutes to get all the shape curves in. However, I would agree that the actual core network, the initial boundaries, can take much longer. This often depends on the quality of the cloud, the complexity of the vessel. It's down to going in and understanding what characteristics to create in in the definition to bring out the actual shape of the vessel. So you'll find that maybe a very small number of curves take quite a long time to get right. I mean, hours instead of minutes. Some of the case studies that this has been applied to, we've done the schooner that we've seen in this presentation, the tug that was seen in the recent example. It's been used in rib molds to redefine a Type 23 frigate, and more recently it was applied to the mega yacht, and that gave us the opportunity to use the validation process. So now we'll have a look at the short demo. So first we'll start by opening a laser model. So here we see the laser model we had earlier in the presentation. Presently this being shown with the colour that was captured in the physical survey, and there was a lot of areas that were quite dark. So what we can do is enhance the colour. And you can see the underside of the vessel now. We can see that areas where the hull form was shiny haven't been captured at all. We also see that we've got some areas of the underwater body which hasn't been captured either. It's not clear why. Some sparse areas around there. So this view gives us an overall visualization of the data that we have. We can also have some local visualizations which we can use for looking in more detail about particular parts of the vessel. So here we'll go down the stem, and we can see we're picking out there with some of the points some of the protection on the bow, on the stem. We'll go along the stem, and we can run to the transom. So doing this kind of thing is quite helpful for picking out the features along the keel, which can often be quite challenging to pick out with geometry. If we go to the transom itself, we can see that we've got some underwater lighting features and other details that would be quite difficult to pick out, and we can make a decision now whether we're going to include them in our design. We can also pick out some of the arrangement of the curves that we're going to deal with. And then we'll need to look at the shape of the hull form in more detail. For that we can use the sections. And this is kind of giving us the 3D contours of the shape that we're going to deal with, picked out in the points that are intersected with the planes that we cut through the model. And this is quite a useful tool. Ultimately this data is the data that's used to generate the curves. So we can make some modifications. We can just constrain this to the port side, for example. These get reprocessed, and we can see all the designs there. We'll move on to just work with the sections. So now pretty much we can have a body plan. And using the body plan, for example, just as a visual view, we'll start to make up the hull surface itself. At this point I'll bring in the curves, the boundary curves, because these take a bit of time to generate. It's quite challenging to find some of the features, particularly in this model, that the features that make the best shape. So it was quite a few hours to make these curves, but you'll see now that once I've got those curves in place, generating the hull form is quite a quick activity. So starting out, we'll use the body plan and generate a diagonal section through it, just to illustrate how this process works. So I'm effectively going to draw a plane. So there we are. We have a section, a diagonal section through the hull there. We can see all the sampled points. We see a gap and more sampled points. Now the display tells me that the mean accuracy of this curve is within 3 millimeters of the scan data, and a max deviation of 21 millimeters. Now I can have a look at the curvature. We can increase the display so we can see how that's doing. So it's pretty good. I can improve the quality of the curvature by introducing smoothing. Obviously, as I introduce smoothing, then the accuracy of the fit to the surface starts to reduce. What you can do is just introduce a very small amount of smoothing, and the curve quality improves very quickly without moving away from the surface too far. But generally, if I'm fitting to a surface, I'll try to work with zero smoothing. You can also see a graphical visualization of the deviation. Basically these lines are indicating, much like the curvature, the relative difference between the curve and the surface itself, and we can enhance that. So what we would do at this stage is pretty much use these displays to determine the number of control points that we're going to use along the length of the vessel, and then once we've chosen a number that works out well, try and stick to it so that each curve has the same mathematical model. So that's a small illustration. We'll now go through the process of generating each of the diagonals for this surface. So we'll fit around five curves along the length of the vessel. We'll start around here, and I'm just drawing these curves. So we'll create the curve there, and we'll just carry on through this process. And we'll make sure that each curve has the same number of points. We'll have a curve here. Sometimes I can pick out two sections, so we'll need to remove that segment and just work with that one there. And we'll have another one here. And a final one posted here. I'll try that again. Here we go. So that is the top one. We'll remove that section and just work with that one, so 10 points. So what we've done here now is created a selection of curves that just trace the shape of the whole form in that area. They all have the same number of control points. They've been done very quickly, so there's a good chance that they won't have a perfect fit. Certainly around the bow of the vessel I would probably go for a different shape, but it's just a quick example. So now we'll need some curves crossing in the other direction, and we'll just trace these as cubic splines. So I'm just putting in quite a few curves, more than I want, but that's because there's quite a lot of diagonals, and I want to keep the aspect ratio of the patches not too high ratio. We'll go through like this, and we'll put one there, and we'll start snapping to some points and pick out the other features. There should be another curve there, like so. So once we've got some curves, now we can generate the surface. Like so. So that's a curved surface based on those curves. We'll now put on the contours to see what we've got there. So now we can see we've probably got a fairly smooth surface, and that's resulting from the quality of the least squares fit, like so. We'll hide the sections for now. There we go. So we can have a look at that in its rendered format and look at the quality from the light perspective, shading on the whole form. So we can see it's got quite a lot of smoothness, but it will diverge towards the challenging areas of the surface because we've really not worked on that. We can also have a look at the curvature characteristics directly. So we'll pop off the contours, and we can see that even though we've spent a relatively small amount of time, we've got a reasonable amount of curvature quality on that. So we have a good surface in terms of its curvature characteristics. Have we got an accurate surface in respect of the laser data? So we can take that forward and do some analysis. So we'll create an object that allows us to compare the surface with the laser scan data. And much like the curvature analysis, this allows us a pictorial view of the quality of the surface. We'll get rid of, again, the curves to come back, so get rid of those. We'll get rid of the mesh, and here we can see we've got some shading. We've got some blank areas where the density of the point cloud is not dense enough to draw a conclusion to the position of the surface, so there's not enough statistical data in that area. We've got some red areas where the tolerance of the surface is outside what's defined. Presently it's defined as 20 millimeters. We can take that to 10 millimeters, go down to 5 millimeters, and the red areas increase as it starts to find the areas of the surface that are outside that tolerance. We can look at that from a sided perspective, so we find that the red areas on one side and the blue areas on the other side. We can also look at the areas of the surface that are within the thickness of the cloud in terms of kind of the min and max normal distances. So you can see, now we can start to see how well we're doing with the metrics of the data itself. So we get quite a lot of feedback, and these are a useful set of tools to present to other people that might not be working on the project, present to the customer, highlight directly how accurate you're getting your surface. So concluding the presentation now with a summary. So presently what we see in a lot of the solutions is that they're kind of disconnected. We have a survey process that captures everything, and then we take this to another system that applies its own knowledge, and really in looking at how we survey the ship and then how we turn that into a surface definition, we're not necessarily carrying through the expertise of the marine domain. And that's the thing, I think by enhancing the solutions that we already have in the marine domain, allowing existing software to connect to cloud surveys, then we're going to get a much better approach because we're using tools that we've traditionally been using for the last few decades. And finally, I think the key thing in this whole thing is the validation process. It makes it so much more of a productive experience. You can quantify the accuracy of the surface rather than having to make a very much a visual decision. Thank you very much.